Today in second year chemistry, we are having one of the most aesthetic or beautiful chapters in physical chemistry, where we discuss in a micro level analysis of the structures of solid substances. Actually, we wonder about the state of a matter, like some matter exists in the form of a liquid, some matter exists in form of a gas, some matter exists in the form of solids at the same temperature. For example, at 25 degrees C, if you observe, at 25 degrees C, if you observe, you just take a flask of oxygen gas, a beaker of water, a bowl of sodium chloride. All are at same temperature, 25 degrees C. But it is our human experience that oxygen definitely exists in gaseous state, water surely exists in liquid state, and that exists in solid state, table salt, gas, liquid and solid. Solid state means what? A rigid state. Suppose I have got some 5 liters of an iron piece with parameters that is fixed. That particular volume of the rigid solid is fixed and the shape is also fixed. You can't make it flexible. In case of a liquid, it is volume is rigid but shape is not rigid. But in case of gas, both volume and shapes are flexible. But first the $1,000,000 question is, why they exist in those states at a given temperature? At 25 degrees centigrade, I think you all are aware of the fact that temperature is a measure of the thermal energy of a system. Every system possesses some thermal energy in the form of heat content of the system. It is a measure of that. That thermal energy dominates the intermolecular forces. Suppose what does oxygen gas contain? Oxygen molecules. The molecular attractions may be there, but they are very weak. What attractions will O2 have? They are not ions, they are not dipoles. At least one of them is a dipole. We may think there may be dipole interactions operating. The thermal energy is there for molecules. Their energy is able to break the intermolecular forces very easily, because intermolecular forces are so weak. So, the molecule will be able to escape individually from the other molecule. It has energy enough to overcome the intermolecular force and escape. But in a liquid state, at the same temperature, the molecular thermal energy is not sufficient to overcome the intermolecular forces. Suppose if you take two water molecules, there will be hydrogen bonding, and this bonding requires some energy to break it. The self energy of the molecule at a given temperature may not be sufficient to overcome this attraction. Then what will happen? Molecules will stay together. Once the molecules stay together, it exists in liquid state. So, the liquid state continues. Of course, if you increase the thermal energy, you make it 100 degrees at 1 atmosphere pressure, the molecules will get sufficient energy to overcome the intermolecular force and escape in the form of vapor. It will go into gaseous state. So, at 25 degrees, the thermal energy of water molecule is not sufficient to overcome the intermolecular forces, so that molecules will not be able to escape from each other as good as in oxygen at a given temperature. So, it will continue to be in liquid state. Coming to this, again same temperature you are observing, at 25 degrees even sodium and chloride will have some thermal energy, but sodium and chloride ions are strongly attracted. This is a tremendous electrostatic force of attraction, very strong attraction. So, it is very difficult to overcome that attraction. The thermal energy required by the ions is too much. At 25 degrees centigrade, sodium plus and chloride will possess some thermal energy which is not sufficient to overcome the intermolecular interactions or inter-ionic strong electrostatic forces. So, what may happen? The ions will stay together. In the bulk of the salt, sodium chloride, there is not a single sodium plus ion and single chloride ion present. You have got many sodium ions, many chloride ions are together in the crystal with strong electrostatic forces, or you can call Coulombic forces, which cannot be overcome by thermal energy at that particular temperature. So, they stay in solid state, a rigid state. It will not freely escape. The ions will not simply escape out like O2 molecules. The ions will not simply roam and move, delocalize like water molecules in water. So, here what you should think is, every system, every state of matter if you take, that will have thermal energy, that will have intermolecular forces, interparticle forces. If interparticle forces dominate the thermal energy, it will try to be in condensed state. The thermal energy dominates the intermolecular forces, it will be in free state like in gas. Condensed state is favored by stronger intermolecular forces. Free state is favored by high thermal energy and weak intermolecular forces. So, when you are moving from a gas to solid, what happens? As you, provided the temperature is same, as you are moving from here to here, the intermolecular forces will become stronger and their dominance over the thermal energy will be more. So, the system is going towards more and more condensed form. Solid is more condensed, liquid is less condensed, gas is totally free. As you move from that to this, what is happening? Here the thermal energy is dominating over intermolecular forces. So, if the thermal energy dominates the intermolecular forces, the system will go into a free state. This is the basic reason behind the reason for why a particular form of matter exists in one particular state, liquid or gas or solid. However, in this particular class, we are not worried about the gaseous and liquid states. We will discuss more and more hereafter about the solid state, which is a multidimensional subject. Many properties of solids can be discussed, and in various structures of solids under this chapter. So, right now out of the three basic states of matter, we are now prepared to appreciate the solid state. So, let us now think of only solid state. Only as I told you, in solid state intermolecular forces are very strong than the thermal energy of a given system. In this solid state, whenever you think, we come across many substances like iron. Suppose I will write some solids. Iron is a solid, Ice is a solid, or you can think of plastic, rubber, iodine, sodium chloride. See, there are many forms of solids we come across. Plastic, what will be there inside? What is there in sodium chloride? You take a hard iron piece, how the iron atoms are arranged in that particular metal form. So, to first before going to appreciate the real structures of solids, we must keep in mind one broad classification. Within solids, we come across two varieties. They appear as solids like crystalline solids and amorphous solids. See, basically solids are of two types: crystalline, amorphous. These are very commonly used English words: crystalline solids and amorphous solids. Here I would like to advise you something. Instead of calling them amorphous solids, we can call amorphous substances. Better than the word solid, it is better we use the word amorphous substance. What could be the basic difference between crystalline and amorphous? They appear to be solids, but amorphous are not regarded or respected as solids. As for appearance wise, they may appear like a solid. Here the basic difference is, whenever you take the bulk of a solid, definitely it is a 3-dimensional pattern. Any solid will have a 3-dimensional occupancy. The particles, every solid is made up of particles, constituent particles. Suppose you have ice bulk, what will it contain? H2O molecules. So, H2O molecules are the constituents of ice solid. Sodium chloride, it has got sodium plus and chloride minus as its constituent particles. Just iron, iron will have only iron atoms or iron ions inside, that is made up of iron only. So, every solid possesses some constituent particles, and those particles are distributed in the space in a 3-dimensional manner. So, what can we decide? A solid is made up of some constituent particles arranged in some 3-dimensional space. Of course, not now. In our next classes, we are going to refer to a beautiful word called lattice. That lattice means the 3-dimensional arrangement of particles in a solid. How good they are arranged and all we will describe later. So, in that lattice, if the particles are nicely systematically arranged in a nice systematic manner, just like how bricks are arranged in a wall, such arrangement is respected as crystalline solid. Crystal means systematic arrangement of particles, systematic 3-dimensional arrangement of particles. But in amorphous, what happens? The particles are just scattered, thrown out. You can't find a systematic arrangement of particles. Suppose I bring some bricks and just dump from a truck. Will the bricks take a systematic arrangement? If I make a wall, it will take a systematic arrangement. So, if you arrange the particles in a most systematic manner, we get a crystalline solid. If the particles are scattered but in solid like state, we call it an amorphous substance. If you dump bricks, it is amorphous arrangement. If you make a wall out of a bricks, it is crystalline arrangement. In a nice way, 3-dimensional systematic arrangement gives crystalline substances. But why they become like that? Simply the same logic. If you dump the bricks from a truck, it takes less time, amorphous arrangement. But to make a wall, it takes more time. You have to construct neatly. When a substance is quickly formed, when a solid is quickly crystallized, suppose 1000 degrees vapor state is there, suddenly you shift the content into a 50 degrees centigrade room, there will be a sudden solidification, during which what will happen? The particles will take Heterogeneous positions, irregular positions, and the substance is condensed in amorphous manner. Whereas at the same 1000 degrees you gradually cool it 900, 800, 750, 700, 650 like, gradually diminish the energy, then the particles will take their best possible position, they will optimize their energy and get crystallized in a beautiful systematic 3-dimensional manner. So, you will get a crystalline solid. So, the quickly formed condensed substance generally gives amorphous substances like rubber, plastic, paper, all those things. Whereas in iron, sodium chloride, diamond, all these things are crystallized in a systematic manner, and we call them crystalline substances. So, in the solids you can have the two basic varieties. Let us go in details. See the beauty of a solid here. How is it happening? There is a nice 3-dimensional arrangement. Just now I called it a lattice. See, in the particles are, this may be anything, that you have violet balls and green balls, they are particles. Those particles are nicely arranged in a systematic 3-dimensional way. We call them crystalline solids. Whereas in amorphous, let us see what happens. See, are the particles systematically arranged? No. See the violet ball, in one region you have one variety of arrangement. Some other region, see how they are crowded. Too much of crowding. Here very less particles within the same substance because of irregular arrangement of particles. It means here you have all nice systematic arrangement like this, but here irregular arrangement. We call them amorphous, we call them crystalline. So, if you want to know the differences between these two, see the first difference, particles are arranged in a regular pattern, particles arrangement is irregular. What do you mean by this? Just now I told you, the particles whatever may be the constituents, generally in a solid what will be the constituents? Sometimes molecules, sometimes atoms, sometimes ions. If they are nicely systematically arranged, you will get crystalline. The particle arrangement is irregular. So far we have been speaking the same concept. Coming to the next difference, anisotropic in nature, isotropic in nature. What do you mean by these words, anisotropic, isotropic? If you observe a crystalline solid from different directions, the observation may be by means of any instrument or whatever, that you do not worry. Basing on the observation, for a crystalline solid the properties would differ. I will show you something here. You have some particles in a solid, crystalline solid. There is one layer of particles, another layer of particles, another layer of particles, another layer of particles. If you are observing from here, you will find some interlayer distance as x, 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 x like. The distance between two layers is x, x, x. Whereas, if you change the direction of your observation, now you see from this direction, this is one layer, another layer, another layer, layer of particles. You come across one more set of planes of particles, and here the interplanar distance need not be again x, it can be something else y. Suppose I change my direction of observation from here, I may come across the interplanar distance to be z. What do you conclude from this small argument? If you keep changing the direction of observation in a crystal, this will not show similar properties, will not show similar properties. If the direction of the particle property changes with the direction of observation, such property is called anisotropy, non-similar. So, the plane properties, crystal structures vary depending on the direction of observation. So, you change it, that will change, we call it anisotropy. But here what happens? Isotropic, because everything is hazardous, everything is like this. So, even if you change the direction of observation, what will happen? Nothing. So, wherever, however you see the particles, I mean the crystal, solid, not crystal, solid, if you change the direction also, nothing will change, everywhere you will see some irregularity. So, nothing is changing, everywhere it is similar. So, isotropic. Be very clear, never be carried away by those words. Anisotropy looks to be a negative word, but in isotropy the particles look, I mean however you see the crystal solid, you will see the same thing. But in anisotropy, the crystalline solids, if you change the direction of observation, the crystal properties, you will come across different varieties of crystal properties. So, this is a very beautiful difference between crystalline and amorphous solids. The third one is a good one, the definition of the same. Crystal properties may vary based on the direction of observation. Here crystal properties may not vary based on direction of observation. This is the definition of that, isotropy. This is the definition of anisotropy. Going to the next thing, it is a real beautiful difference between crystalline and amorphous substances. Possesses sharp and definite melting points. What do you mean by melting point? The temperature where the crystal gets collapsed, that solid state is lost, the solid will become dismantled. As I told you, if you raise the temperature, thermal energy will increase. As the thermal energy increases, the particles escaping tendency will increase, the solid state may be lost. In crystalline substances, what happens? Suppose you have a crystal, the particles are systematically arranged as per our earlier discussion. See how nicely they are arranged. Assume I cut one piece from this part. I will take this piece and observe the melting point, happens to be x. Now, I will cut one more piece from elsewhere, from here. I will observe the melting point, it will be x only. What do you understand? Irrespective of where you cut the piece and try for the melting point, you get the same melting point. Sharp melting point, suppose 320 degrees means 320, whether you cut a piece from here or here. Why it happens like that? Because the forces are uniform. If you cut a piece from here, whatever the intermolecular forces are prevailing, whatever is the distribution of the particles present in this part of the crystal is same as the same distribution of particles observed elsewhere. Forces are identical, forces are uniform, interparticle forces are similar. the behavior of the crystal is uniform throughout its bulk. So, whenever you take a piece of it and observe it, it will sharply melt at one particular melting point. As a matter of fact, melting point is a measure of purity of a substance. What happens in this case? The particles are non-uniformly distributed. Suppose I cut a piece out of it, the particle distribution is not same as this. See, this part has more particles, that part has less particles. If I cut this from here, I cut a piece and test for the melting point, I will get something, and if I cut from here, I will get something else. Why it is happening like that? Because the distribution of particles and the balances of the forces, the intermolecular forces are not identical in different parts of the substance. So, it has no melting point, proper melting point. Some student will cut this point and say some melting point, some other student will cut the other part and report some other melting point. Okay, this particular substance has this particular melting point, like that we cannot tell. Whom should we blame? Blame the non-uniform distribution of particles. So, that is another kind of a feature what we can differentiate between crystal and crystal substance and an amorphous substance. Coming to the next point, long range orders of particles are observed. You take a crystalline solid like this. So, particles are systematically arranged. Whatever you see here, you will see here also. Long range orderliness. If you find some order somewhere, it is the same order till the end of the crystal. That orderliness of the particles do not change. Long range orderliness. That is why you can always claim, you cut one small piece at this edge of a solid and observe it, you can claim that you have observed the entire crystal. No need to travel all the way. Once you take a big iron piece, at this end, whatever micro level particle you take and observe, all features are repeated throughout the bulk of iron metal. Long range order, particles are similarly distributed in the entire bulk, but whereas the observed patterns of particles short range, you see some pattern in one place, immediately the pattern may change. You may think, okay, this is the pattern, this is the pattern of distribution of particles, but somewhere else it may not be same. The pattern of arrangement of particles keeps changing from one place to other place. So, we call it short ranged patterns. True solids and supercooled liquids. Actually, solids means crystalline solids, that is it. They are only true solids. You can't claim them to be solids in amorphous case. We should call them supercooled liquids. Supercooled means they are just dead like, but still they have liquid kind of non-uniform distribution of particles. So, we call them supercooled liquids, and these are true solids, crystalline solids. Just for fun, I gave some examples: copper, iron, sodium chloride, ammonium bromide, diamond. These are all very good examples of crystalline solids. And plastic, paper, rubber, glass, all these things come under amorphous non-uniform distribution. Now, tell me, in our chapter we are interested in that or this? Obviously, because we can't systematically study anything in amorphous substances, so we do not show much interest on that. So, our interest now, crystalline substances. So, how the crystalline solids show their properties and what are their structures, what are the features in crystalline solids, we will try to understand in the rest of the chapter. Now, let me tell you one thing very clearly. Crystalline solids, as I just told you, they follow some 3-dimensional pattern, because no solid is just 2-dimensional. 3-dimensionally they are arranged. Suppose in your house you see table salt, sodium chloride. What will sodium chloride contain? Obviously sodium ions and chloride ions. But how are they present in the lattice, in the solid? Actually, if you assume a 3-dimensional view, a quite general 3-dimensional view I am drawing, just some 3-dimensional picture. Any solid, it can be long, short, left, right, do not worry about that now. My interest to show this is to make you feel that 3-dimensional view. By seeing this, can't you feel 3-dimensional? So, there is a top face, there is a bottom face, there is a left face, there is a right face, back face, front face. So, to represent a 3-dimensional space I drew this, that is it. What I am telling, once you have a crystalline solid, any solid will have particles, constituent particles. Those particles are distributed like this in a 3-dimensional manner. Suppose I show a particle like a circle, see how the circles are. Sometimes they may be here. We will discuss so many things, wait. Particle distribution, they are distributed in the space. Now, first of all, why are they together? Why are they together? Just now I told, in a solid the particles are tightly held, intermolecular forces are strong, their energy is not sufficient to escape from this. So, they are held together, that is why we are able to visualize it as a solid. Now, what make them together? There is a forces of attraction. So, if you take any crystalline solid, you will see some constituent particles nicely distributed in the space and held together with some forces. Basing on these two concepts, we divide crystalline solids into 4 varieties. See the systematic approach what we are doing. First I took matter. I said there will be 3 kinds of matter, basic kinds, gas, liquid, solid. I forgot liquid and gas, I took only solid matter. What did I do? Solid is again distributed into what? 2 varieties, crystalline solids and amorphous solids. Again I have ignored amorphous. Why? Because the particles are non-uniformly distributed. So, I have thrown them into dustbin. I have taken only crystalline. Now, I am analyzing only crystalline and now telling there are 4 varieties of crystalline solids. On what basis did you classify the crystalline solids? On the basis of the particles and the forces. A solid must have constituent particles, the particles which build up the solid, crystalline solid, through 3-dimensional systematic arrangement and with some forces of attraction, they are held together. Now, this particle which I am just showing as a circle or a sphere can be a molecule, it can be an ion, it can be an atom, like that. That is called a motif that keeps repeating in all the entire crystal. And based on the particles which are making the solid, we classified the crystalline solid substances into 4 varieties by name: metallic solids, ionic solids, molecular solids, covalent solids. By seeing the names itself you can decide. Metallic solids means what? All metals. All metals adopt crystal structure. Ionic solids, they are also solids but the particles are ions. Molecular solids, the particles are molecules. Covalent solids, the particles are atoms. Atoms are held together by bonds. That we will discuss for some time now. Now I have taken only crystalline solids, 4 varieties. Metallic solids. What do you expect from metallic solids? What is an example? Metals. Lithium, sodium, potassium, rubidium, cesium, francium to scandium to zinc, D block, F block. You have so many metals in nature. I think 3/4 of periodic table is metals only. What is the, suppose a kid is asked what is the difference between metal and non-metal nowadays, he easily answer. A metal atom possesses less valence electrons, more vacant orbitals. A non-metal atom possesses more valence electrons, less vacant orbitals. Metal is vacant orbital rich and non-metal is valence electron rich. I am speaking about a metallic solid. Metals are electropositive, so they lose their electrons while forming a solid. Suppose you take a metal atom, many metal atoms make the solid metal. Each metal atom first loses its own valence electrons or loosely held electrons, and what will be created in a metal ion? There will be vacant orbitals created. All these vacant orbitals will be there. Electrons lost by the metal atoms will make a band continuum. We call it electron gas, we call it electron sea, we call it electron cloud. But what is most important is, whatever name you call it, that electronic cloud keeps on delocalizing. Delocalizing across what? Then many vacant orbitals. That electron cloud makes a band or sea or a, whatever you call it. It is a delocalized cloud, dynamic cloud, kinetic charge that keeps roaming throughout the metallic crystal. After losing electrons, ions are left. Those ions are embedded here and there in the crystal in a 3-dimensional pattern. So, metal ions are embedded in an electron sea like this, a big delocalized electron cloud. The attraction between the metal ions and the cloud is electrostatic, Coulombic force of attraction, which keeps the metal very tight and hard. That attraction is called metallic bond. If this electron density is very high and the metal ion is small, the attraction is more. The metal will be very hard. If the metal ion is big, electron cloud is weak. That metallic bond is weak metallic bond. Such metals are easily bent, soft, you can cut them like. See, in S block what happens? Metal ions will be big, they have 1 or 2 valence electrons, they lose those electrons and make the electron cloud. Metal ion size is big and electron cloud is less dense, metallic bond is weak. So, S block metals are soft, easily sublimable. You can cut sodium metal with a knife, whereas iron, chromium, tungsten very hard. In D block, metal ions are small. After losing those electrons, the electron cloud is very thick. The metallic bond is very hard, very strong. So, those metals are very hard. So, whatever may be the case, if you take any metal, you have to visualize there is an electron sea, there is an electron cloud, where here and there in a 3-dimensional manner metal ions are embedded. So, electrons keep moving, so they are very good conductors. So, these are metallic crystals. What are the repeating units? After losing electrons, each metal will have a core. That core ion is systematically arranged in a 3-dimensional pattern called lattice. And what type of force is keeping them together? The attraction between those metal ions and the electron cloud, Coulombic force, will keep the metal intact. So, it will be very hard. That is a metallic crystals. Second variety is ionic crystal. Name itself is telling. In the crystal arrangement, 3-dimensional arrangement, the repeating particles are what? Ions. You may have Na plus, L minus, forward, left side, right side, backward. In a 3-dimensional manner, the ions are nicely distributed, optimizing their repulsive forces and attractive forces, where attractive forces dominate over repulsive forces, and finally some energy is lost and the crystal is stabilized. And such crystals where ions are taking the relative positions in the lattice, we call them ionic solids, ionic crystalline solids. Here the particles are ions, the forces are electrostatic forces of attraction, Coulombic forces. Covalent crystalline solids. What do you mean by covalent crystalline solids? I told you, in a solid, crystalline solid, particles are nicely distributed in 3-dimensional way. Suppose somewhere you have a non-metal atom. This is a non-metal atom. What does a non-metal atom do? It forms covalent bonds. So, this may form some covalent bonds like this, here, here, here. And this non-metal atom will again form some covalent bonds, or this non-metal may form some other covalent bonds. See, it is a big system containing so many non-metal atoms held together by strong covalent bonds. If you want to break down this crystal, what to do? Spoil a crystal. How to dismantle a crystal? Increase the thermal energy. So, raise the temperature, you break all the bonds. Very difficult, because a network solid, forward, backward, so many covalent bonds you need to break. That is why such solids will have abnormally high melting points. Here also, if you want to dismantle, the solid, what to do? Thermal energy should be raised. If you take sodium chloride, table salt, and heat it to around 650, 700, the lattice will be broken into free ions. Thermal energy dominated the intermolecular forces, interparticle forces, intra-ionic forces. So, diamond, graphite all come under covalent solids. Molecular solids. See, covalent and molecular, you should be very carefully differentiating by means of structure. In molecular solid, the lattice points are occupied by molecules. Wherever you have the arrangement of particles, the particle is basically what? Molecule. This is also a molecule. How two molecules are held together? Why are they in solid state? The molecule can attract another molecule. By what forces? Van der Waals forces, dipole forces, or hydrogen bonding, but all are weak. Within the molecule you may have covalent bonds, localized entity, but between two molecules what do you have? Some weak forces. Now is it easy to dismantle that lattice or not? Very easy to dismantle or break that particular lattice, because the molecular forces are very weak. Dipole, ion dipole, dipole, hydrogen bonding, Van der Waals forces, London dispersion forces, like very weak forces keep them together. Once you raise the temperature to a small extent, the thermal energy will dominate the intermolecular forces and break down the crystal. In third group periodic table you have boron, aluminum, gallium. Boron's melting point will be in thousands, aluminum melting point will be in hundreds, gallium melting point will be in tens, 29 degrees or so. All this trend, thousands, hundreds and same group, you have to appreciate their crystal structures. Gallium is a molecular solid, Ga2 molecules are held together, aluminum is a metallic solid, boron almost like covalent solid, very difficult to break the covalent bonds. So these are the basic 4 varieties of crystalline solids. We will see them in more detailed way in my next point. What type of solid you want to see and what are the repeating particles and what forces are keeping the particles together, general melting point range. See, iron melts at a high temperature, diamond melts at 3500 above, but ice melts at 1, 2, 3 degrees is enough provided 1 atmosphere pressure. So that melting point range also we can appreciate, we will see one by one. So as I told you, in metallic solids, what are the forces operating? Metal ions in electron gas. See, metallic solid, suppose you take lithium plus, a big pattern, each lithium has lost one electron, all those electrons together make a gas like this. Now you can see the next column, metal ions in electron gas. So delocalized electron cloud where the metal ions are embedded, that is a repeating unit, that metal ion only you will find. And what are the forces? Electrostatic force of attraction or Coulombic force, better word. So these ions attract the electron clouds. There will always be attraction between the ions and the electron cloud. Negatively charged electron cloud and positively charged ions attract together, so the ions won't escape. So Coulombic forces of attraction, stronger those attractions, harder the metal, weaker those attractions, softer the metal. So lithium, small ion in some electron cloud, cesium, big ion in same electron cloud. Obviously what will happen? Electrostatic force is less in cesium. So cesium melts at a lower temperature than lithium. The metallic bond in lithium is stronger than in cesium. Electrostatic force that coming, generally moderate, I said moderate to high you can say. Little high, that actually depends. Just now I told you lithium, cesium, both are monovalent, their electron cloud is of same magnitude or density is same almost, but lithium ions are very small embedded in the electron cloud. Small ions attract the cloud in a more greater extent. So, lithium is a harder metal and cesium ion big, embedded in such same quantity of electron density, and the electrostatic force is weak. So, it is a soft metal. So, lithium is hard, cesium is soft because of the difference in the metallic bond. So, they show different melting points, but generally in metallic solids you see moderate to little higher melting points. Ionic solids. In ionic solids, examples also there are metals copper, iron, sodium, potassium kind, sodium chloride, magnesium oxide, whatever, ammonium bromide also you can take, like, who are held together, oppositely charged ions. If you take an ionic solid like your table salt, potassium bromide, oppositely charged ions are embedded and they are attracted to each other through strong electrostatic forces, strong Coulombic electrostatic forces, and for them also the melting point will be moderate to high depending on the lattice energy. See, ions come from infinite distance. In first year chemical bonding you have studied, form a lattice. In that particular lattice, the operating forces are very strong. The net repulsive and attractive forces, if you take, the net force is very high, more energy is lost. The more energy lost, the more stable is the, strong is the crystal. Greater the strength of a crystal, melting point will be obviously more. So, it is moderate to high. Suppose lithium fluoride, cesium iodide, both are ionic compounds only, very good ionic compounds. But here ions being very small, attraction is very hard, that is very high. So, melting point will be high, here melting point will be low. So, generally that is why I said moderate to high. Coming to third variety of solids, covalent solids, non-metal atoms, covalent bonds, abnormally high. A covalent solid is formed by whom? Non-metal, see diamond, SiO2, silicon carbide. For example, you have one silicon, it is attached to 4 carbons, and again carbon is attached to silicons. It keeps on going like this. See, so many covalent bonds within the crystal. So, what may happen? If you want to dismantle this, you have to break every covalent bond. But covalent bond is strong only. Breaking a covalent bond, so requires lot of energy. So many covalent bonds. That is why we call them network solids. So many covalent bonds in the 3-dimensional network formed by non-metal atoms. So obviously their melting points will be extremely high, abnormally high. Diamond, graphite, SiO2, carborundum, boron carbide, we have got many covalent solids. The entity which repeats is an atom, not a molecule. So that is why the melting points are very high. Coming to next variety, molecular solids. I just showed you, in a molecular solid, the particles are what? Repeating particles will be molecules. Wherever there may be different positions, we will discuss in next class. Here the molecules will be there. How the molecules are held together? They are held together by either hydrogen bonding, like in ice. In ice, what is happening? Water molecules are held together through hydrogen bonding. Suppose you have xenon solid, xenon atoms are held together by van der Waals forces. Solid iodine, I2 molecules are held together. Phosphorus P4, So, molecules are held together by weak van der Waals forces or dipole-dipole interactions or hydrogen bonding. So, what did I write here? Very low melting point of ice, very less. If the 1 atmosphere is there, it will melt at even 1 degree, 2 degrees also. Just now I told you boron aluminum case. Boron has I think more than 1000, aluminum less than 1000, gallium is 29 degrees or 30 degrees melting point. Why such a low melting point of gallium? I gave Ga2 here, Ga2 molecule. In the crystal, all gallium molecules will be held together. So, it is very easy to melt it. So, among all varieties of crystalline solids, which solids are the hardest solids? Which solids possess highest melting point? Covalent solids. Covalent solids possess abnormally high melting points because in covalent solids the repeating unit of particle is an atom. Atoms are held together by covalent bonds, the non-metal atoms preferably, and these are also called network solids. Their melting points will be abnormally high. Diamond, graphite, sand, carborundum, boron carbide, just now I told. Which will have least melting points? Molecular solids. The repeating particles are molecules. Molecules are held by weak van der Waals forces or hydrogen bonding, whatever. So, it is very easy to dismantle the lattices, the crystal structures of molecular solids. And finally, these metallic solids and ionic solids possess moderate to high melting points depending on the case. Suppose alkali metals may possess low melting point, transition metals may possess high melting point. Like that in ionic solids also, as I told you, lithium fluoride, both ions are small, the attraction is more, melting point is high. Cesium iodide, the attractions being weak, so melting points are low. So, this is how we will have to use our common sense while deciding the strengths of the bonds operating among the particles in the crystalline solids. Now, I would like to tell you something. What next we can think of these crystals. So, we have decided solids, amorphous, crystalline, we ignored amorphous, we took crystalline. Within crystalline we got 4 varieties of solids: metallic solids, ionic solids, covalent solids, molecular solids. That is okay. Now, I always used one word, the particles will be repeating in 3-dimensional manner. The 3-dimensional arrangement is called lattice. You can also say space lattice. In the space, how the particles are arranged. Here you need to learn some new words: space lattice, crystal system, unit cells, crystal planes like. I would like to just highlight one point before committing to original solid state structures and all. Just observe this 3-dimensional diagram, do not name it anything, just enjoy. Suppose particles are distributed in the space like this. I do not want to name anything, just take the 3-dimensional diagram. So, this is one plane on which you have got particles. This is another plane on which you have got particles. So, you are able to see the 3D picture, 3-dimensional picture of a solid. It need not be like this, we have got varieties, we will discuss in the next class. See, from here to here there is some distance. From left face to right face there is some distance. From top face to bottom face you have seen, from left face to right face you have seen, from back face to front face one more distance. So, the planes are separated by certain distances, and also what is the angle between bottom plane and this plane? Some 90 degrees, and like that you can worry about even the angle between the planes. So, we have got in different varieties of crystalline solids interplanar distances, interplanar angles. Based on this and based on geometrical limitations, all solids in the earth and heaven must come into any of 7 varieties of crystal systems. Any solid you take, let it be iron, let it be metal, let it be ionic, let it be covalent, let it be molecular, you take any crystalline solid, it must fall in any one variety of 7 well defined crystal systems. To understand that, of course, the systems are classified on the basis of interplanar distances, interplanar angles, keeping in mind the geometrical, spatial restrictions. So, those 7 crystal systems we will have to define, and each crystal system we have got certain patterns, varieties of repeating parts called unit cells and such parameters, that we will discuss in our next session. So, I wish you have a good day today. So, keep thinking of whatever we discussed in today's class. Read any standard book, make your own notes and copy down when I teach.